Module 10, Section 8.3, Conditional Probability, Intersection and Independence. Objectives. Objective 1, be able to calculate conditional probability. Objective 2, be able to use the product rule to calculate the probability of the intersection of two events. Objective 3, be able to construct probability trees. Objective 4, be able to determine if events are independent or dependent. Conditional probability. Let's consider the experiment of rolling a fair die. Let A be the event of rolling a prime number. So then A consists of the outcomes 2, 3 and 5. Let B be the event of rolling an odd number. Then B consists of the outcomes 1, 3 and 5. Suppose we want to calculate the probability of rolling a prime number if it is already known that the outcome is an odd number. This is called a conditional probability, and we write it as P A given B. It is read as the probability of A given B. Let's see what this number is going to be. The probability of A given B is equal to the number of outcomes of A and B divided by the number of outcomes of B, because we already know that the outcome B has happened. So when we divide by the number of outcomes in the sample space, we can convert this to a probability form. That is the probability of A and B, or A intersection B, divided with the probability of B. So this formula, probability of A given B equal to probability of A and B divided by probability of B, helps us to calculate the conditional probability. In our example, the probability of rolling a prime number, given that an odd number has already shown up, is equal to 2 divided by 6 divided by 3 divided by 6, which is equal to 2 over 3. So numerator is the probability of rolling a prime number and an odd number. There are two outcomes like that, which is 3 and 5. And the denominator is the probability of rolling an odd number, which will be 3 out of 6. So this is the formula for the conditional probability. The probability of an event A, given that an event B has already occurred, is equal to the probability of the intersection of the events A and B divided by the probability of the event B alone. Notice that we are writing this formula P of A given B equal to probability of A and B divided by the probability of B. Here probability of B is not equal to 0 because we are dividing with that. Here is an example. There are two majors of a particular college, nursing and engineering. The number of students enrolled in each program is given below. A single student is selected at random. We need to find the answers to the following questions. What is the probability of the student selected is a nursing student? So we will write this as probability of nursing student, which is the event N. There are 100 nursing students, and there is a total of 150 students. So the probability of getting a nursing student will be 100 over 150, which is simplified as 2 over 3. What is the probability of getting a graduate student? There are 60 graduate students, and out of 150 we will get 60 over 150, which is equal to 2 by 5. That is the second answer. The third question, we are calculating the probability of a nursing student and a graduate student. So this is the intersection, and probability of N intersection G. So we need to look in the nursing row and the graduate column. So N intersection G is going to be equal to 47, this number up here. So there are 47 nursing students who are also graduates. So we need to divide 47 over 150 to get the answer to this probability here. Probability of N and G. Probability of getting an engineering student and a graduate student. So which is the probability of E and G. So there are 50 engineering students, of which 13 are graduates. So we need to divide 13 over 150. Continuing with the same problem, suppose we are given that an undergraduate student is selected at random. What is the probability that this student is a nursing major? So restricting our attention to the column representing the undergraduates, we find that of the 90 undergraduate students, 53 are nursing majors. So we write this as the probability of nursing student given that it is an undergraduate student, conditional probability. So according to our formula, it will be probability of n and u divided by probability of u. So probability of n and u will be 53 over 150. So we will get 53 over 150 divided with the probability of getting an undergraduate student will be 90 over 150. So when we cancel this 150, we will get the answer to be 53 over 90. Suppose we are given that an engineering student is selected and we need to find the probability that the student is an undergraduate student. So this time we need to restrict to the sample space of 50 engineering students. 37 of the 50 are undergraduates. So we can calculate this probability as 37 out of 50. So which is also the same as probability of undergraduate and engineering. So undergraduate and engineering will be 37 out of 150. That is the probability of P U intersection E. Then I need to divide with probability of getting an engineering student. There are 50 engineering students, so it will be 50 divided by 150. When we simplify this fraction, we will come up with 37 over 50, which is 0.74. Here is another example. From the given probability table, find the probability of C intersection D. So C intersection D will have a probability given by 0.03 because we are looking at the common value for D and C. So we need to look across the D row and the C column. So this answer will be 0.03. So the next question will be calculating the probability of D given C. So we need to write the formula. Probability of D given C will be probability of D intersection C divided with probability of C. That is the formula for the conditional probability. Probability of D and C is the same as 0.03. That is our earlier answer. Notice that C intersection D is the same as D intersection C. Both the events are the same. Divided with probability of C will be the column sum for C, which will be 0.20. It is calculated up here. So that will be divided 0.20. So once we do this, we will get the answer to be 0.15. The third question, we are calculating another conditional probability. Probability of B given E. Probability of B given E equal to probability of B intersection E divided with probability of E. So probability of B intersection E is the value 0.25. So that is, we are looking at the row corresponding to E and the column corresponding to B. So we will get the intersection coming out to be 0.25 probability. Divided with probability of E. Probability of E is the row sum corresponding to E, which is calculated here as 0.80. So 0.25 by 0.80 will become 0.3125. So that is the conditional probability of B given E. Let E and F are events with the probabilities. Probability of E equal to 1 by 5, probability of F equal to 1 by 6, and the probability of E and F equal to 1 by 7. So we need to calculate probability of E given F. So this is again probability of E intersection F divided with the probability of the conditioning event, which is F. So we will get 1 divided by 7 numerator divided with probability of F will be 1 by 6. So when we do this, we will get 6 over 7. Notice that the denominator is a fraction, so we need to multiply with the reciprocal. So this is the answer. And to calculate the probability of F conditional to E will be probability of F and E divided with probability of E. The numerator is again the same, 1 over 7. Denominator is the probability of E, which is given as 1 by 5. So again, when we divide these two fractions, we will get 5 over 7. Here is another example. For the month of March in a certain city, 88% of the days are cloudy. Also in the month of March in the same city, 20% of the days are cloudy and snowy. Notice the and here. What is the probability that a randomly selected day in March will be snowy if it is a cloudy day? Let's take the event C as cloudy day, and let's say S is equal to snowy day, just for convenience. If we read the question, we need to find the probability that a randomly selected day in March will be snowy, conditional to the day being a cloudy day. So that means we can write it as probability of getting a snowy day if it is already known that it's a cloudy day. So that will be probability of S given C. So probability of S given C will be probability of S intersection C divided with probability of C. S intersection C means it's a snowy day and a cloudy day. The probability of that is given as 0.20, 20%. So we divide this with probability of C. That means the day is a cloudy day. There is a chance of 88% for the day to be a cloudy day. So that means divided with 0.88% will be written as 0.88. And we can write it as a fraction 5 over 22. Here are some important formulas. Probability of A given B is equal to probability of A intersection B over probability of B. We already know this. So if we cross multiply this, we can write it as probability of A given B multiplied with the probability of B equal to the probability of A intersection B. So we have a similar formula here, that the probability of A intersection B will be equal to, in terms of the conditional probability, that will be probability of A given B multiplied with the probability of B. And in the other form, that will be also equal to probability of B given A multiplied with probability of A. So this is the important formula that you need to be paying attention to. Now we can look at what is called probability trees. Here is an example. Two machines are in operation. Machine A produces 60% of the items, whereas machine B produces the remaining 40%. Machine A produces 4% defective items, whereas machine B produces 5% defective items. An item is chosen at random, and then what is the probability that it is defective? So we are trying to answer this question. What is the probability that a randomly selected item is a defective item? We can represent this situation using a probability tree. So we have two ways an item be produced, either through machine A or machine B. So the probability corresponding to machine A is 0.60 or 60%. So that is used as the label for this edge here. So this probability is 60% or 0.60. Probability of B will be 0.40 or 40%. So that is the label for the other edge. Now once you come to this point up here, there are two ways the product can turn out. If it is coming through machine A, there is a 4% chance that it be defective and the remaining 96% that it be good. So we are going to label this edge as having probability 0.04 and the other edge as probability 0.96. And the same thing with the machine B. Coming to this edge, we have a 5% chance that the product be defective and 95% chance that the product be good. So each of these edges will have a corresponding probability labeled. Now to get a defective item, it can either be coming through machine A or it can be through B. So we are going to write it as probability of defective equal to probability of getting a defective through A and probability of getting a defective through B, which is A intersection D and B intersection D. Notice that they are disjoint, so therefore the probability can be simply added. Once we use the conditional probabilities, we can write probability of A intersection D as probability of A multiplied with probability of D given A, and also probability of B intersection D is written as probability of B multiplied with probability of D given B. Now probability of A is clear from this tree diagram, which will be 0.6, and probability of D given A means that the getting a defective item if it is known that the product is produced through machine A. So that is given in the question, which is 4% or 0.04. So we are going to use 0.04 as the conditional probability here. And when we put the other numbers here, we will get the answer to be 0.044. So in terms of the probability tree here, we simply multiply 0.60 and 0.04 and add to 0.40 and 0.05, the product of 0.40 and 0.05. There is another example. Use the table below to find the indicated probabilities. Here the events A, B, C are mutually exclusive as well as the events D, E and F. What is the probability of A and what is the probability of C? These are the two questions. Because A is disjoint from B and C, the probability of A is actually the addition of the A column. So if you add all these three values, we will get probability of A and D, which is probability of A and D or DA, and probability of A and E, probability of EA, then probability of F and A, so which is the third number here, which amounts to adding the probabilities in the A column, getting an answer equal to 0.70. It's already been added here. This is the column total. Likewise, the probability of C will be the same as adding the probabilities in the C column. Because C is again disjoint from B and A. So we only need to add the probabilities in the C column to get the probability of the event C. Independence of events. Two events are independent if the probability of A given B equal to the probability of A. This means that the probability of A does not depend on the occurrence of the event B. Probability of A is the same as probability of A given B. In the same way, probability of B given A equal to probability of B will also imply that the events A and B are independent. Also, if the probability of A intersection B is equal to the product of the probabilities of A and B, then the events will be independent. All these three statements are equivalent statements. If the events are not independent, then we will say that they are dependent events. Here is an example. Test the pair of events A and D for independence based on the following probability table. So we have the definition: two events A and D are independent if the probability of A intersection D is equal to the product of probability of A and the probability of D. Probability of A intersection D is, we need to look in the D row and the A column, which will be this 0.21. So A and D or A intersection D will have a probability 0.21. If we calculate the probability on the right side, we need to compute the probability of A. So probability of A is the column sum for A, which will be calculated here as 0.70. So this number is 0.70. Then you need to multiply probability of D. So probability of D will be the row sum, which is calculated here as 0.30. So this number is 0.30. So let's see whether this equation is true. If we multiply 0.70 with 0.30, we are going to get this as 0.21. So we get this to be true. So this is satisfied. So the answer will be A and B are independent. Here is a summary of the main formulas that we found in this section. We have the formula for the conditional probability. Probability of A given B equal to probability of A intersection B over probability of B. And likewise, we can also write probability of B given A equal to probability of B and A or B intersection A divided with probability of A. Then again, if A and B are independent, then the probability of A intersection B will be equal to the product of the probabilities of A and B. Probability of A times probability of B.